Let's move on to question 2. So we have a semicircular wire, and on one end we step an object, a bead, and it goes down to the other end. And we are asked about the force that the bead applies on the wire. So this is the first source of error that some students might make. They might calculate the normal force on this bead and take that to be the answer. The normal force on this bead, whatever it will be the force applied by the wire on this bead. The force applied on the wire by this bead will be equal and opposite by Newton's third law, so you'll have to reverse the direction for the answer. So first we'll calculate the normal force, then we'll figure out the reaction force, which will just be the opposite of that. Now initially when you leave here, it's going to the right, but its acceleration is 0, right? Because its speed is 0, start with 0 speed, so v square by r in this direction is 0, that means mg is equal to n. So initially the normal force is radially outward. By the time it reaches this point, it has some speed, so it actually has a component of force in this direction, which actually gives it mv squared by r, right? And obviously gravity is vertical, so this has to be the normal force. So even qualitatively, we can see that initially the normal force is radially outward, at the end it is radially inward, so it makes sense that there must be some point at which it changes its direction. And we see the options: always radially outward, always radially inward, or initially outward, finally inward, and vice versa. So it seems to us that it should be either C or D, because initially the normal is radially outward and finally the normal is radially inward. So let's just try to solve it rigorously at any random point theta. Let's assume this is the normal force radially outward. It's either radially outward or radially inward because it has to be perpendicular to the surface. This is mg, this is theta. So the equation in the radial direction is mg cos theta minus n is equal to mv squared by r. Right. But another equation would be, if the speed is 0 here and here is v, we can conserve energy between these 2 points. So the work done by gravity, which will be mgr times 1 minus cos theta, because initially it is at a height r, then this is r cos theta, so what is left is r into 1 minus cos theta is equal to half mv squared. So if you put this in this equation, you take 2 to the other side and you take r to this side, you get mv squared by r is 2mg into 1 minus cos theta. So mg cos theta minus n is equal to 2mg times 1 minus cos theta, which gives us n is equal to, this is 2mg and this is 3mg cos theta. So 3mg cos theta minus 2. Initially theta is 0, so it is mg. That means it is positive, so radially outward. Finally theta is pi by 2. This is minus 2 mg. Finally theta is pi by 2, so this is 0. So this is minus 2 mg. That means radially inward. Because we've assumed radially outward, the negative normal force means radially inward. So we get that the normal force is out. Actually, we got this qualitatively as well, but I just wanted to show you that at cos theta is equal to 2 by 3, which is some angle in between 0 and 90, the normal force becomes 0, and then it changes direction. Right, that's not explicitly asked in the question, but just for the sake of explanation. So initially the normal force is radially outward, finally the normal force is radially inward. Some students might look at this and put in option C, but the actual answer is option D, because remember what is asked in the question: the force which the bead applies on the wire. If the wire applies this force on the bead, then the bead applies this force on the wire. So on the wire it's radially inwards initially and radially outwards finally. So the answer is option D.